Welcome back, everyone. Today I'll talk a little bit about the group structure of the Rubik's Cube, but first we have to start by talking a bit about permutations. So a permutation is just a reordering of some set, and typically we use just the numbers 1 through n for our set. Last time I mentioned the notion of a bijection, and a reordering is just the same as a bijection from the set to itself. So let's say we have the set, I'll call it S, and we just have the numbers 1, 2, and 3. We could represent a permutation as a function from the set to itself. In this example, let's say 1 gets sent to 2, 2 gets sent to 1, and 3 just stays there. And this is a function, so we can actually combine two permutations together using function composition. So let's say we have a second permutation, and this time we'll send 2 to 3, and we'll send 3 to 2. So this means the second thing in the ordering, this means the third thing in the ordering, and then this time 1 will just get sent to itself. So instead of writing it as composing two bijections, we can just write it as a single function like this. So here 1 started out going to 2, and then it ends up at 3 because it went from 2, then 2 goes to 3. So this time 1 will go to 3 here. Then 2 goes to 1 and stays there. And then 3 goes to 3 and then to 2. So this is the composition of these two functions. So we could say this is f and g. And then this represents g composed with f. And when we write this with function composition, if we have f of x, then g of f of x is the same as g composed with f of x. And when we write that, we do f first and then g. So that's why we write f first here and then g, meaning we do f here and then we do g. So if we choose some set, then we can get a group by just looking at all the possible permutations of that set, using composition as our binary operation. And you can check all the group axioms are satisfied if you want. For convenience, we'll just call the permutation group on a set with n elements the symmetric group on elements, or just Sn, like this. It doesn't really matter what you call the elements in your set when it comes to the permutation group. It really just matters how many elements there are, which is why I said at the beginning that we generally just use the numbers 1 through n. Now, commonly the way that we'll write an element of a permutation group is we'll open parentheses and we'll write all the elements of the set up here. And then let's say we're doing this here, so we'll say this is equal to g composed with f. On the bottom here, we'll write where the elements end up on the right hand side. So 1 gets sent to 3, so underneath 1 here we'll write 3. Then 2 gets sent to 1, so we'll write 1 underneath 2. Then 3 gets sent to 2, so we'll put 2 here. So this is the common way that we write the elements of Sn. I'll do another example here. We'll take two permutations. We'll say tau here is the permutation. Let's use 5 elements, so 1, 2, 3, 4, 5, and tau is this permutation. And then we'll take another permutation, we'll call it sigma. And sigma, it also has to be on 5 elements, and this time it'll be this permutation. And then we want to compute sigma of tau. And instead of writing a circle here, we'll just write sigma tau, because it's clear, since we're talking about permutations, what putting them next to them means. That this just means composing them. And remember, this means that we do tau first, and then we do sigma afterwards. So this is, well, I'll just write them out again. And if you work this out, remember we start here. So if we work this out, we start with tau. So in tau, 1 goes to 3, and then 3 goes to 5. So 5 will go here. Then we can work all the rest out similarly, and we'll get this permutation here. And you can come up with lots of examples to practice using this notation. And I think your homework will be on this as well. Now I want to go on a brief tangent, so I'm going to talk about the symmetries of an equilateral triangle. So pretend that's an equilateral triangle. Let's number the vertices, so 1, 2, and 3. So if we, okay, this is one symmetry we can do. We can flip it along the vertical axis, and that would result in the triangle 1, 3, 2, like that. And then we could also flip it along any of the other axes. And then we could also rotate it counterclockwise or clockwise. And those are all the symmetries of a triangle. And it actually turns out these actually correspond precisely to the permutations of 3 elements. So this would be just the permutation where you do nothing. This one, we swapped 2 and 3, so this would be 1, 3, 2. This one we swapped 3 and 1. And this one we swapped 2 and 1. And this one, we cycled them, so. And then this is just the reverse. Actually, I think I got these two mixed up, so just swap those two. But in any case, this actually is an example of what I talked about last time, which was an isomorphism. So it turns out that S3 is isomorphic to the symmetry group for all the symmetries of a triangle. Now, maybe this is a general thing, so maybe Sn is the same as symmetries of an n-gon. But we'll actually run into issues with that for anything larger than 3. So, for example, for a square, if we number them 1, 2, 3, 4, in S4 we have this permutation here, where we swap the first 2. But for symmetries of a square, we can't just swap 2 of the vertices and keep the other 2 the same, because it wouldn't remain a square that way. So the symmetries of a square are a subgroup of S4, but S4 is not the same as symmetries of a square. And this turns out to be a very general thing. Any group can be represented as a subgroup of permutations. And this is called Cayley's theorem, in case you want to look it up and read a proof. So how does this apply to the Rubik's Cube? Well, with the Rubik's Cube, when we make turns, we're permuting the edges and we're permuting the corners. You can't have a corner swapping with an edge, though, unless your cube malfunctions in some way. So what we can do, we'll call our elements C1 for corner 1, C2 for corner 2, and so on, up to corner 8. So we'll have those permuting with each other. And then we'll have E1 for edge 1 up to edge 12. In this case, it would be a subgroup of permutations of 20 elements, where the first 8 elements don't swap ever with the last 12 elements. But that's not all, because we could have something like this, where here everything is permuted correctly, but these two are twisted, so we also have to worry about the orientation of the pieces. So we can add an orientation. So with the corners, each corner has 3 stickers, so we need to have 3 things for each corner. So I'll have 1, 2, and 3, and we'll have a subscript, so C1 for corner 1. And then we would also have that for all the rest of the corners. And it actually turns out, for reasons that we'll discuss next time, we actually only have to worry about 7 of the corners. So I'll go up to corner 7. And just pretend this is on the same line. I'll put it down here. Then the edges each have two stickers. So we can have something like this where we have those flipped. So the permutation is still the same. And I guess we could still have the corners twisted, but in this case we wouldn't be able to account for that here. So we also have to pay attention to the edges. And here we'll have to have one number for each sticker on the edge. So we'll have 1 for edge 1 and 2 for edge 1. And the same for all the other edges. And again, we actually can ignore the last one, so we only need to worry about 11 of the edges. And then permutations of those elements are how we can represent the Rubik's Cube, except each collection of elements with corresponding subscripts only interact with each other. They don't interact with the rest. So this is how we can represent the Rubik's Cube as a subgroup of a permutation group. Although usually we don't have to write it all out like this, but it can be useful to have this in your head for how it's all working.